The beginning of chapter 6 had a lot of review from Algebra 1, but the end of chapter 6 starts talking about some new things, and specifically we look a lot at functions. So, let the fun begin. Let's do a little warm-up, pause the video, and see if you can remember how to find h of 8. So remember this function notation h of 8 means wherever I see an x, I'm going to replace that with an 8, and then follow the order of operations. H of 8 should give you 40. What does domain mean? This is a big part of this lesson. Domain, recall, means all possible inputs. So if I look at the first function, I'm looking at what are all possible x values that I could square and then subtract 3 times that number. The domain of this function h would be anything, negative infinity to infinity. So domain restrictions, there are some cases where the domain can't be anything. It can't be a negative infinity to infinity. So let's look at some various types of functions. I want to find the domain of the following functions, or in other words, what x values would produce real number outputs. So the first one, hopefully you recognize it. This is just a parabola. So this negative 1 would move the graph y equals x squared down 1. So your vertex would be at 0, negative 1. What could I plug in for x? Well, if you remember back to semester 1, this is just a polynomial. So if I have anything like x cubed, x squared, x to the 4th, I should be able to plug in any real number for x and square it and then subtract 1. So the domain is all real numbers, negative infinity to infinity. Or if you wrote something like this, same thing. Just for the fun of it, let's look at the range. So the domain's anything because it continues left and right forever. However, if I scan up and down, there is a low point. So the smallest y value that will come out is negative 1, and then the parabola opens upwards. So this would be the range. Second one, if I look at this function, what do you remember about this graph? Y equals 1 over x is a hyperbola. This should kind of look similar. This is going to produce a hyperbola because you have the 1 over x. So the hyperbola, the parent function, y equals 1 over x squared, looks like this. Let's take a look at the graph of 1 over the quantity 8x plus 2. So I inputted this into the graphing calculator. Let's see. And there's your hyperbola. Do you notice how you have a vertical asymptote? So the question is, where is that vertical asymptote at? Or what can't x be? Well, for the parent function, we'd say, well, I can't divide by 0. So the domain would be anything except x values of 0. That was the vertical asymptote. And the range was any value except 0 for y could come out. But if I look at the 8x plus 2, what's really happening? Well, if I have a fraction, here's one domain restriction that you're going to have to start looking at. It is not possible to divide by 0. So whenever I have a fraction, I need to look at the denominator and say, hey, that denominator cannot equal 0 because I don't want to divide by 0. If you go through and solve, you'll see that x cannot be negative 2 over 8 or negative 1/4. So on the graph that we drew of this function, x equals negative 1/4 would be your vertical asymptote. Therefore, your domain, I can plug in anything for x except negative 1/4. And that's what that interval notation is saying. If I want to look at the range, it looks like anything is coming out for y except if I can't divide by 0, there's no way I could get out 0 for y. Let's look at two more functions. The next one, g of x equals the square root of x plus 6. Well, if I'm wondering what could I input to get real number outputs, I cannot take the square root of a negative. Otherwise, I'd be in imaginary number land. So if I'm looking at any function that has that square root, I'd be thinking, well, whatever's under the square root would have to be greater than or equal to 0. So if my index is even, this stuff under the radical can't be negative. So I go through and solve this, x would have to be greater than or equal to negative 6. And that's actually your domain. So if you left it like this as an inequality, that's okay. If I asked you for interval notation, I'd want to include negative 6. So negative 6 would be the smallest number I could input here. to get out a real number answer. Think about it, square root of negative 6 plus 6 is a square root of 0, which would give me 0. Anything smaller than that would produce a negative number under the square root. So negative 6 to infinity is your domain. If I looked at the graph of this function, can you see how the furthest to the left this graph goes on the x-axis is negative 6? Anywhere beyond that, I'd get a negative under the square root, and I'd get out an imaginary number. The last function, t of x equals the square root of x all over the quantity x minus 4, this really combines the two things that you need to be looking for when you're considering domain restrictions in this lesson. So the first one is the square root. Can't take the square root of a negative and get out a real number. So the first thing I'd be thinking is, well, my inputs have to be greater than or equal to 0. Otherwise, that would cause a negative value for your radicand. The second thing is I have a fraction. So whatever's in the denominator, this cannot equal 0 because I can't divide by 0. So for the denominator, x minus 4 cannot equal 0. If I solve this equation, x cannot be 4. If I input 4 here, 4 minus 4 is 0, I can't divide by 0. So if I combine these two ideas, here is your domain and interval notation. This is saying I could plug in any value for x 0 or above except 4, and I should be able to get out a real number output. And remember, this sign in the middle just means union, so either the x could fall in this interval or this one. Any of those would be possible inputs for x. Here's just a look at that last graph, kind of interesting. Your vertical asymptote would be at x equals 4. The graph can't touch that line. And the furthest to the left the graph goes is an x value of 0. So in 6.6, we're going to start looking at function operations. The first two we're going to look at is adding and subtracting. So if I tell you something like this, f plus g of x, that essentially just means take function f of x and add it to function g of x. If I'm subtracting them, similar idea, f minus g of x would be the same as saying take f of x and subtract g of x. Now a note, the domain of the sum and difference functions consists of the x values that are domains of both functions. So let's take a look at what that means. First example, let f of x equals 4x plus 7, g of x equals the square root of the quantity x plus 3 plus x. And what is f plus g of x? So f plus g of x, this would be the same as saying what is f of x plus g of x? So if I'm finding the sum, all I have to do is take f of x, 4x plus 7, and add on g of x, square root of x plus 3, plus x. And then if I'm adding, just combine your like terms. So in the end, f plus g of x equals 5x plus 7 plus the square root of x plus 3. Do you want to give part B a try? So let's see if you can find the difference, f minus g of x. Pause the video, give this a try. Okay, so let's see how you did. If you're subtracting, most common mistake, I am subtracting all of g of x. So did you distribute that negative to each term and actually get out 3x? It's 4x minus x, or 3x plus 7 minus all of that stuff. So make sure you're subtracting each term that's in g of x. The last thing, let's look at the domain. So if I go back to the previous page, on the bottom, the domain, I have to consider the domain of both functions if I'm adding or subtracting. So if I go back to the top, the first function's a line, so my domain should be anything. I can plug in anything for x, take it times 4, add 7, and get out a number. So domain of x, or domain of f, excuse me, all real numbers can be inputted into function f. For g, however, I have this restriction of, I have a square root. So what real number inputs could I put in to get real number outputs? Well, x plus 3, whatever's under the square root has to be greater than or equal to 0. I can take the square root of positive numbers, I can take the square root of 0, and that will produce real number outputs. So if I go through and I combine these ideas, the bottom one, x plus 3 is greater than or equal to 0, x plus 3, if I subtract 3 from each side, you get x has to be greater than or equal to -3. So if I input -3 plus 3 would give me 0. That's the smallest real number I can plug in to get a real number output. So the total domain for the sum or different functions, either of these functions, I'm looking at only problem is I cannot take the square root of a negative. So my domain would be -3 to infinity. So now, let's look at multiplication and dividing. If I have two functions that I multiply or divide. One important note for tomorrow, if you see this dot, or in the future, I should say in this chapter, if you see this dot, that just means multiply. So if it's a closed dot, it means multiply the functions. So if I have f times g of x, it'd be the same as if I multiplied f of x times g of x. If I see f divided by g of x, it's the same as saying f of x divided by g of x. But here's the note. The domain and product of the domain of the product and quotient functions consists of the x values that are in the domains of both functions, but there's an additional restriction here, and does not contain any x value for which g of x equals 0. So kind of like if I was adding or subtracting, I want to look at the domain of both functions, but if I'm dividing, I cannot input something that would cause me to divide by 0. So example, I have function f of x and g of x. Let's see if you can come up with what the product would look like. So pause the video, see if you can determine the product f times g of x. So if you multiplied it, hopefully you just distributed, did some FOILing. This is a cubic, so if you remember algebraics, your degrees odd, leading coefficients positive. Your graph would look something like this. It goes left and right forever. Since this is a polynomial, I can certainly plug in anything for x. And take x and cube it and square it, multiply it by numbers, and I should be able to get out real numbers for y. Let's take a look at f of x divided by g of x. So if you divide, you'd have x squared minus 9 over x plus 3, and maybe you realized, oh, this is a difference of squares. You could factor the numerator. There we go. Factor the numerator. And then since you're multiplying those terms in the numerator, you could cancel. And in the end, if you divide these, the most simplified form is f of x divided by g of x should just equal x minus 3. So let's take a look at the graph. So my graph, here's my function. And yeah, I get y equals x minus 3. So from the graphing calculator, you might be thinking, well, I mean, I got a line, my domain's anything. But what you can't see is that -3, there's actually a little hole where the graph doesn't exist. So you need to go back to the beginning before you canceled any factors. Way back here, the denominator cannot equal 0. So for my original function before I canceled anything, x plus 3 can't equal 0. If I solve that, x cannot equal -3. So my domain for the quotient function would be I can input anything for x except -3, because g of -3 would give me out 0 in the denominator, and I can't divide by 0. So maybe you're thinking you've got this. I just want to provide you with another example if you want to look at it. So if you feel like you might need an extra example, give this a try and we'll compare. Find the domain of function h, find the domain of function f, and then find the domain of the quotient of each of the functions, f divided by h and h divided by f. Pause the video, give it a shot. First function's a line. It's a polynomial. I can plug in anything for x, subtract 2, and get out a real number for y. So domain, all reals. Second one, you do have that square root, so I can only take the square root of 0 or positive numbers to get out real numbers. So the domain, if you put one of these, both of those would be correct. Anything greater than or equal to 0 for your inputs. So here are your quotient functions. The first one, if I look at the numerator, okay, x has to be greater than or equal to 0. So I've been looking at this, but then in the denominator, I can't divide by 0. So along with this idea that x can't be negative, because I'm taking the square root of x, I also want to combine that x cannot equal 2, because 2 minus 2 would cause me to be dividing by 0. So with those two thoughts in mind, my domain of f of x divided by h of x would be any real number greater than or equal to 0, but not including 2. Second one, if I'm looking at the numerator, no problems. I can plug in anything here. Domain of that function was all real numbers. In the denominator, however, I have two things going on. So I have the square root. So again, I can't take the square root of a negative. And I can't divide by 0. So I'd be looking at, well, the square root of x minus 10 cannot equal 0. So if I solve this, the square root of x cannot equal 10. And then the square root of what number would give me 10? If I square each side, that would be 100. So x cannot equal 100, because if I inputted 100 in the denominator, I would have the square root of 100 minus 10, or 10 minus 10, which would give me 0, and I can't divide by 0. So for h of x divided by f of x, my domain, I can't have any negatives because of this piece, and then I also can't have 100 because that would cause me to be dividing by 0.